This research paper introduces a novel approach to website fingerprinting, WF, a technique used to identify websites visited over anonymized connections by analyzing patterns in network traffic flows. Prior WF approaches have limitations, including characterizing WF as identifying specific web pages rather than entire domains, relying on unrealistic attack models, and lacking diverse training data. The proposed method, WF-Net, addresses these limitations by classifying entire websites, using a convolutional neural network, CNN, that operates on jitter and packet size features from any point in a TCP stream. WF-Net is trained on traffic data collected from various network environments, including cloud data centers, universities, and home networks. The results show that WF-Net achieves over 90% accuracy in identifying websites, outperforming traditional WF attack models such as QML, DLWF, and triplet fingerprint. The accuracy of WF-Net is attributed to its ability to generalize across different network environments and its robustness to variations in packet size and jitter. The paper highlights the importance of having a comprehensive training set that is representative of various network environments. It demonstrates that domain adaptation can maintain accuracy when training traffic is acquired at different network points from the training and testing sets. This is achieved by modifying the network training phase to add an auxiliary network that classifies locations, which helps retain features related to website classification while eliminating features related to locations. The paper also discusses the limitations of prior WF approaches, including their reliance on heuristics to find page boundaries and their unrealistic attack models. The proposed seamless WF attack model relaxes these assumptions, allowing the attacker to observe 500 contiguous packets anywhere in the TCP stream. The results show that this approach significantly increases the difficulty of attacks. Overall, this research paper contributes to the field of WF by introducing a novel approach that addresses the limitations of prior art. The proposed method demonstrates the power of CNNs in WF and highlights the importance of having diverse training data and domain adaptation to achieve high accuracy. Here is the combined summary of pages 3 and 4 of the research paper. The authors present a study on website fingerprinting attacks, which aim to identify the websites a user is visiting based on network traffic patterns. They introduce two approaches to evade these attacks: inflation, which adds randomization delay and inflates packet sizes, and active injection, which adds extra packets at random. However, they find that inflation is not feasible for existing applications, while active injection requires significant protocol changes. The authors then provide an overview of related work in traditional network traffic classification, highlighting various machine learning and statistical approaches. They note that these methods often rely on monitoring and analyzing packet timing and size characteristics. Recent studies have leveraged deep learning algorithms to enhance the accuracy and efficiency of website fingerprinting attacks. The authors also discuss the limitations of existing website fingerprinting methods, which primarily rely on monitoring and analyzing packet timing and size characteristics. They highlight the importance of considering multiple environments and diverse datasets to ensure robustness. The paper presents a novel approach using domain adaptation techniques to improve the performance of website fingerprinting attacks. They introduce a neural network structure that incorporates domain indices to mitigate differences among domains. This approach enables the model to smoothly transition between domains during continuous domain shifts. The authors also provide a comparison of their dataset with traditional datasets, highlighting the diversity and complexity of their dataset. They emphasize the importance of considering multiple environments and diverse datasets to ensure robustness. The table on page 4 provides a comparison of network characteristics across different locations, highlighting the variability in interpacket intervals, packet sizes, and browser bandwidth. The neural network structure implementing domain adaptation is also presented. The authors highlight the importance of considering transfer learning, domain adaptation, and backdoor learning techniques in website fingerprinting attacks. They note that these techniques can enhance the performance and generalization capabilities of website fingerprinting models. The WF-Net base architecture is presented in Figure 3, showcasing a novel approach to website fingerprinting. Table IV highlights the accuracy of WF-net base when trained on one location and tested on another, demonstrating its robustness across different environments. Prior research has demonstrated the vulnerability of machine learning models to backdoor learning approaches, which can manipulate output by injecting malicious data into the training dataset. In the context of website fingerprinting, clients can improve privacy by altering their traffic patterns, reducing the accuracy of trained models. Traditional website fingerprinting, WF, has several limitations, including closed-world modeling, sequential browsing, isolated traffic, replicability, traffic parsing, passive web page, disabled cache, static content, and single web page. These assumptions limit the practicality of WF in real-world scenarios, as they require controlled environments or laboratory experiments. The proposed approach addresses these limitations by visiting most or all subpages of a website to represent it comprehensively. The dataset, on average, visits over 20,000 unique subpages per website, providing a more realistic representation of website fingerprinting's effectiveness in real-world conditions. Modern browsers and technologies have shifted from discrete page interactions to continuous user engagement, influencing web traffic patterns. The proposed approach simulates a wider range of user actions using Puppeteer, capturing the complexities of modern web usage more accurately. The majority of public datasets process complete packet sequences into single-page packet sequences, padding them with zeros to uniform lengths. However, this padding introduces additional distinguishing features that significantly aid classification. The proposed approach sidesteps this issue by classifying at the entire site level rather than individual pages. Figure 4 illustrates the distribution of padded zeros in the AWF 775 dataset, showing a near-linear relationship that enhances predictive models. However, padding zeros is unrealistic and leads to an overestimation of website fingerprinting efficacy in practical scenarios. The approach also considers the impact of network environment and computing power on traffic features, which prior work often overlooks. Factors such as physical location, ISP providers, and client capability significantly influence traffic features and must be taken into account. In the realm of website fingerprinting, a novel threat model has been proposed that is better suited for the era of streaming media. This model assumes that classification can be effectively achieved with fewer packets, 500 fixed-length packets to be precise, as opposed to the state-of-the-art 5,000 packets. It also considers frequent user interactions, subpages, page advertisements, and other elements as representations of the website's traffic. The methodology employed for synthetic trace generation involves using a browser to access a set of known websites. Packet traces were recorded at 1-minute intervals, and the data was processed into feature vectors. The dataset was composed of 42 websites collected in a university setting, with 20 websites collected from 8 different environments. The networking and execution environments used in this study include a university, cloud, and cable home setups. The university environment utilized 2 Dell R7525 computers located in a campus data center as clients, while the cloud service providers rented dedicated CPUs situated in 5 cities across 3 countries to serve as clients. Cable home environments were also used, with Hewlett-Packard PCs equipped with Intel i7 4770 and Intel Core 2 Quad Processor Q6600 connections. The model structure, WF-net base, consists of 17 convolutional layers connected to 3 fully connected layers, with batch normalization after each convolutional layer to enhance adaptability to different input data. The model's design includes 5 residual blocks, each employing a residual connection strategy to connect the first and last layers, resulting in superior performance when dealing with complex data. An expanded version of the model, WF-net large, was also developed, which achieved higher accuracy in the mix location task. The dataset was collected using Puppeteer, a library for remotely controlling a browser, and T-Shark for gathering PCAP files at 1-minute intervals. This data collection was achieved through monitoring 2 ports, yielding a total of 60 files, with these files being overridden by new data on an hourly basis. The actual performance of a single core of the Intel Xeon processor is roughly half that of the AMD EPYC Milan architecture, and the single-core performance of the server is similar to that of the Cloud 3 server. In this research, we delve into the realm of website fingerprinting attacks, which exploit packet-level information to identify websites visited by users. Our primary focus is on developing a novel deep learning model, WFNet, capable of accurately identifying websites from traffic data across diverse network environments. This model leverages convolutional neural networks and residual connections to enhance its performance. We evaluate WFNet's performance in three distinct attack scenarios. A. The attacker has precise knowledge of the victim's environment. B. The attacker knows the range of environments the victim may use. And C. The attacker has no prior knowledge of the environment in which the victim browses. Our findings indicate that WFNet outperforms existing state-of-the-art models, achieving an average accuracy of 91.4% when the attacker has precise knowledge of the victim's environment. To further enhance WFNet's adaptability, we employ domain adaptation techniques. This approach allows the model to learn domain invariant features, thereby improving its performance when tested on data from unfamiliar locations. We train WFNet on data collected from various locations and achieve exceptional accuracy, exceeding 95%, when the model is tested on data from all scenarios. Our evaluation also explores the impact of increasing the number of websites and training samples on accuracy. We find that while increasing the number of websites and training samples can lead to higher accuracy, it also introduces potential overfitting issues. Furthermore, we demonstrate that WFNet can maintain high accuracy even when utilizing single data features, such as packet interval time or packet size. Finally, we propose several feasible defense mechanisms against seamless website fingerprint attacks and test their effectiveness. These include adding noise to traffic, altering packet sizes, and introducing randomness in packet intervals. Our results show that these defenses can significantly reduce the accuracy of WFNet, highlighting the importance of considering such countermeasures in real-world applications. Here is a combined summary of pages 11 and 12 of the research paper. To assess the capabilities of website fingerprinting, WFP, attack models, two closed-world tasks were designed within a university dataset. The results show that conventional attack models, such as QML and DLWF, yield accuracy rates below 30% for classifying 10 websites, which significantly drop to approximately 20% when increasing the number of websites to 20. In contrast, the triplet fingerprint algorithm achieved a 75% accuracy for the 10 website task. To improve stability and generalization, a deeper CNN model was employed, achieving over 90% accuracy in both 10 and 20 classification tasks without a discernible decline in accuracy as the number of labels increased. The applicability of this attack strategy was evaluated across various network environments. The results demonstrate that, given a substantial training dataset, the model consistently achieves an accuracy rate above 90% across all datasets, emphasizing the potential for accurate attacks when attackers possess detailed knowledge of the victim's network settings. To explore the potential for attackers to conduct predictions across multiple environments simultaneously, the traffic from 20 websites in all 8 locations was amalgamated into a single dataset. The results show that, with sufficient data for preliminary training, attackers could develop a model with robust generalization capabilities, enabling seamless attacks on victims across multiple scenarios. However, the analysis also reveals that the distinct contributions of different environments and the implications of collecting training data in one environment and applying it in another are not well understood. The results highlight the challenges in cross-environment generalization, with accuracy falloffs when transitioning across cloud providers. The impact of the number of websites on accuracy was also explored, showing a very stable accuracy as the number of websites increases from 10 to 40. Furthermore, the correlation between the number of sample vectors utilized and the resultant accuracy was examined, demonstrating that once the count of vectors per site surpasses approximately 50,000, accuracy plateaus at a mid-90% range. Finally, the effect of utilizing a training set that is 9 months old was examined, revealing that the foundational WFNet model witnesses an accuracy decline of roughly 10 to 15 percentage points. However, the application of domain adaptation techniques moderates this drop in accuracy, maintaining it within a 5 to 8% margin. In this research, the authors demonstrate the potential for deep neural networks to identify individual websites using only packet inter-arrival time and length, highlighting a privacy risk even when employing encryption and VPNs. They develop a novel CNN, WFNet, which achieves high accuracy in identifying websites based on these packet characteristics. The authors emphasize the importance of collecting traffic traces from diverse environments, including cloud computing providers, a well-connected university server, and cable modems from private homes, to achieve high accuracy. Domain adaptation techniques are also explored to reduce the impact of network environment on CNN accuracy, allowing for good accuracy in locations without training data. The authors then evaluate the efficacy of two strategies attackers might employ to enhance their attack models in unfamiliar settings. They introduce inflation, which adds a randomized extra delay in bytes to existing traffic, and active injection, which involves the insertion of a randomized set of extra packets into the data stream. Both methods significantly reduce the model's accuracy, with inflation requiring an average of 50x delay and data size to reach a 5% accuracy, and active injection dropping the website identification accuracy to 6% with a trigger size of 35 packets, adding only a 6% increase in average delay and a 2% increase in total data size. The paper concludes by discussing the implications of their findings for privacy protection and the potential for using evasion techniques such as inflation and active injection to safeguard user privacy. These techniques involve adding randomization to traffic features, contaminating the data to reduce ML model accuracy. The authors suggest that the incorporation of triggers can significantly alter the ML model's label predictions, thereby enhancing privacy. The study's findings are relevant not only for TCP streams running over HTTPS but also for newer protocols like QUIC and HTTP/2. The research paper explores the concept of website fingerprinting, where identifiable patterns in website structures can be detected at the TCP and IP levels using machine learning models. The authors found that using both jitter and packet size resulted in high classification accuracy, while using either alone resulted in a few percentage accuracy drops. This suggests that website structures, such as template usage and advertisement placement, likely result in identifiable patterns at the packet level. The authors propose a potential strategy for preserving privacy by allowing protocols to add randomized data within the protocol, making it unclear to attackers whether the traffic is randomized or not. This approach could enable a range of privacy-preserving techniques based on randomized injection techniques without altering the protocols themselves. The paper also discusses the connection between website structure and the patterns seen at the packet level, raising important questions about understanding this relationship. One potential approach is to create cloned sites with altered features to better understand which website structures map to which traffic patterns. The authors provide an extensive list of references, citing various studies on website fingerprinting, network traffic classification, and machine learning techniques. These references highlight the complexity of the topic and the need for further research in this area. The paper concludes by discussing the limitations of the current study and potential future work. The authors suggest that exploring the connection between website structure and packet-level patterns could lead to a better understanding of how to preserve privacy from attackers who can observe system-level timing and size events. Key terms and concepts discussed in the paper include website fingerprinting, the process of identifying patterns in website structures at the TCP and IP levels using machine learning models. Jitter and packet size, features used to classify website traffic patterns. Randomized data injection, a potential strategy for preserving privacy by adding randomized data within protocols. Cloned sites, a proposed approach for understanding the connection between website structure and packet-level patterns. Overall, the paper contributes to the understanding of website fingerprinting and its implications for privacy preservation, highlighting the need for further research in this area.